Let's go over Activity 4. So in Activity 4, you're going to be studying relationships between auctions that have occurred on eBay, specifically for Xbox 360 units. So the first thing you have to make sure that you've done is to have the activity4.rmd file and this file that you need to download off of Blackboard into your BAS 320 folder. And you're making sure that your current working folder is the 320 folder. You'll notice that mine is not, so I need to go and set the working directory to be that 320 folder. And for me, I keep things really organized, so it is in Activity 4 here. All right, so once we are in the correct folder, we're going to read in the data. So I'm going to complete this code that's been partially placed here for us and just put in the name of the file. Remember, read.csv is going to take data from a file and store it into R. We use the left arrow and then we give the data a name. And when we do this, it will appear over on the right in the global environment. So we can see that here are the variables in this data set, a preview of some of the numbers. There is data on 149 auctions. All right, so the first thing we're asked to do is to make a scatter plot to examine the relationship between price and bids. So the first thing we need to think about is, okay, which is our y variable and which is our x variable? Y is the quantity we want to predict, and x is the quantity used to make those predictions. And in this case, I say that the variable of interest is price. Makes sense. We're probably curious about predicting prices based on properties of the auction. And so my y variable in this case is going to be price. So I give you a little bit of a reminder for how the plot syntax works. Basically, we give it the name of the y variable, twiddle, and then the name of the x variable. And then we say what data frame the data live in. All right, so we can make the scatter plot. Resize this window to make it a little bit bigger. And the question is asking us, is this relationship appropriate to model with a simple linear regression? And the key thing is that the stream of points needs to be well described by a straight line. The trajectory of this stream of points can't have any curvature or any sort of nonlinearity to it. And in this case, I look at this stream of points and I see a bunch of outliers. I may have some heteroscedasticity where the vertical spread depends a little bit on where I'm looking here. But I don't see any sort of global curvature in the stream of points, so I would say that, sure, it's linear enough. I don't really see any sort of, obvious relationship, but I don't see any nonlinearity, and so that's going to be good enough for us. So I will say that, yes, the trajectory is linear enough here. There's no hints of curvature, at least. There may be some other issues going on, but there's no curvature, so linear regression is a good approach here. All right, so we're going to go ahead and fit the linear regression model, and the syntax for that is to come up with a name for your model. And by default, I always call my models capital M. You can come up with another name. And the syntax is just like what we used in plot and just like what we used in associate. The name of the y variable, in this case price, twiddle, and then the name of your x variable. And since we're predicting price from bids, that's going to be our name. And then we're going to say what data frame that the data lives in. So this will run and fit the model. You'll notice that over here there's something called M, which is the results of fitting that model. And we'll see what's inside that model in a second. The first thing that I want to do is to add the regression line onto the scatter plot just to see what it looks like. And so I actually have that code for you. Abline M is going to take that model once it's been saved to the name M, and then just add the line corresponding to it onto the scatter plot. So I'll click and run this. That's what our regression looks like. And then I want to add a line for the naive model where basically we say, all right, bids gives us no information about price at all. If we wanted to predict price, let's just use the overall average in the data. That's what the naive model says. And so I'm going to go and add a horizontal line at the value of just the average price in the data. All right, so our regression model does have a noticeable tilt to it. I do see that, okay, there does seem to be a somewhat positive relationship between price and bids. It's not very strong. I see a lot of scatter in the relationship. The relationship isn't very obvious here, but maybe there's something to model. So let's take this a step further. So we know the relationship is weak because this line isn't tilting all that much. There's a lot of scatter, but it does fit the data better than the naive model, the flat horizontal line that just says everything is just the average price. And we can get an idea for how much better the regression fits the data than the naive model by running the ANOVA command on the model. And this will show us what the sum of squared errors are for the naive model, for the regression model, etc. So I'm going to run ANOVA, and that'll give us the analysis of variance table. That's what ANOVA stands for. And what we're asked to report is the sum of squared error of the regression model. And the sum of squared errors of the regression is just the sum of squared residuals of the regression model. And so we see that this number is 550 or 535,000. The number itself, not all that important, but the most interesting thing is how much the sum of squared errors has been reduced when we use the regression instead of the naive model to make predictions. And that's the number right here, actually. If we look at the name of our x variable and we look under the sum of squared column, this is telling us the reduction in the sum of squared errors when we use the regression instead of the naive model. So, all right, we still have a lot of error left over, but we have reduced the error compared to the naive model by a bit. And so we'd like to know, is that impressive? Do I really need to have a regression to model the relationship here, or could I get away with just the naive model? And that's going to be the role of possible regressions. Possible regression is going to do something kind of interesting. Let me run this command and then talk about it. So when I run possible regressions, I get the scatter plot and then the fitted regression line in red. And then what happens is that the permutation procedure runs behind the scenes, basically randomly pairs up together the observed prices and the observed bids, and fits the regression line on that permutation data set. By design, there's no relationship between price and bids in those data sets because they've been randomly paired together. And this gray envelope of lines you see are the regression lines on 100 different permutation data sets. So anything inside this envelope is something that we would expect to see just by chance alone because we've designed those data sets to be like that. And so we see the observed regression line actually is a little bit different. It has a steeper slope, implying that, okay, there is something about our regression model that is helping us to predict price versus just what you would observe from a random chance predictor here. And in fact, we can compare the sum of squared error reduction when using the regression instead of the naive model to the sum of squared error reductions that we would observe just by chance, basically the reduction that we get during the permutation procedure from these lines on the permutation data sets. And we see that this reduction is really out of line with what would happen just by chance. In fact, the p-value of the regression, the fraction of those permutation data sets that happen to fit the data better than our regression line, is essentially 0. We never actually saw that over the course of 100 permutation data sets. So, does it look like price is better predicted by bids than by a random unrelated predictor? Absolutely. So, the regression has a steeper slope than lines that would occur by chance. Notice that the red line's well outside the envelope here, the lines that we see with this permutation procedure. And the sum of squared error reduction is much larger than the SSEs that occur when predicting the price from unrelated random predictors, which we see from the permutation procedure. So yeah, it does actually look like this regression model is doing better than no model at all. It's not a very strong relationship, it's not a fantastically useful regression, but there is something there for us to model. All right, so question 5 says that, yeah, regression predicting price from any unrelated random variable here will always give some reduction in the sum of squared errors. That's what we see here in this histogram of the chance reductions. The question is whether the reduction of our regression model is large enough to be convinced that there's something there to actually model, that BIDS is doing a better job at predicting price than just some random unrelated predictor. So we check to see the p-value of the regression to determine if the regression itself is statistically significant. So quote the p-value of the regression from the ANOVA table. Well, we have an estimate from our permutation procedure here, but a more accurate p-value can be found from the ANOVA table, and we see that it is this number underneath the PR greater than F column here. And so we see the p-value is very small. If I rewrote this as a decimal, 1, 2, 3, 4, 4 zeros, and then a 627. So since this is less than 5%, so the regression model is statistically significant. We're unlikely to see a line that's this tilted, just by chance alone. It's really indicative of some sort of relationship going on that we are able to model here. All right, so what does our regression model look like? Well, we have our straight line. What are the properties of it, the intercept, the slope, etc.? Well, we can run summary on our regression model to get all the interesting information out of here. So we can run summary m, and we're asked to report the intercept, which is just the number under the estimate column in the row labeled intercept, so it's about 98. The slope, that's going to be the number underneath the estimate column in the row corresponding to our x variable, which is just bid, so 1.77. The standard error of the slope, well, that's the number just to the right of there under the column STD error, so about 0.42. The RMSE, the residual standard error, as referred to by R, or the root mean squared error, the typical size of the residual, so about 60.36. R squared, the percentage of variability in selling prices that can be attributed to our model. R refers to that as multiple R squared, so we see that is 0.1036, or writing that as a percentage, 10.36%. And finally, the p-value of the regression, well, we've already reported that with the ANOVA. You notice that it also appears at the very bottom right with p-value. Okay, so there we go. Now, we see that the slope of the regression line on a sample, what we measured just from our small sample of auctions here, will probably be close to the truth. So if we had a census, and a census here would be all auctions that ever involved the Xbox 360 unit, whatever least squares regression line we would fit on that data set is what we call the population regression line. The slope of that line is what we refer to as beta 1, essentially the truth, what we're trying to estimate here. And the value that we get out from our regression line, the slope measured, is going to be close to the truth, but we expect, to be off by a little bit. We're never going to measure the truth. We're going to be close, though. So what we'd like is a confidence interval for the truth for beta 1 based on the data that we've collected. So what we're doing here is actually switching the variables a little bit. Instead of predicting price from bids, predicting price from bidder rate. So let's go ahead and fit that model and see what we can say about the slope. So I'm just going to copy and paste instead of typing this out. The data is still in the Xbox data frame. So we can run it. And I can just look to see, okay, well, what is the measured slope here? The measured slope is minus 0.06. So it looks like that auctions that get sold to bidders with higher ratings actually go for a little bit less than auctions sold to bidders with lower ratings. Maybe those bidders with higher ratings, they've used eBay a little bit more. They're more savvy. They know how to work it to get lower prices. But we know that this estimated slope here is going to be off from the truth, and we want to come up with a range of values of the true slope that seem to be consistent with what we've measured. And so the command that we can do that is confident. Confident is going to give a confidence interval for the parameters in our regression model. So we say the name of our regression model, and then we say, what's our confidence level? And by default, it's usually 95%, so level equals 0.95 here. So I'm going to delete these comments, and I'm going to click Run. And so I see, well, first of all, I asked for 95%, but I'm getting 2.5% and 97.5%. Why is that? Well, in between those two numbers is 95%, so that's where that 95% is. And I look at the row corresponding to the name of my x variable. And so I can say that I'm 95% confident that the true slope is somewhere between minus 0.188 and 0.066. So the 95% confidence interval for the true slope is, and then I'm going to put in parentheses to represent this as an interval, minus 0.19 up to 0.07, a little bit of rounding. Okay, so what is this telling me? Well, I have a good guess of what the slope is from the data that I've collected. I know that that guess is going to be off from the truth by a little bit, and we've been able to figure out, how far off my measured slope might be from the truth. I'm 95% confident that the true slope is somewhere inside this interval. And what I'll notice is that 0 is inside this interval. And if the slope is 0, that implies there's no relationship between price and bidder rating. And so 0 is a plausible value for the true slope. Any number inside this interval is a plausible value for the true slope based on the data that I've collected. And so if 0 is a plausible value and there's no relationship, then I'm not able to say the relationship with this variable here is statistically significant. So the relationship is not statistically significant here since 0 is inside the confidence interval. So 0 is a plausible value for the true slope, which would mean there is no relationship between the variables. All right, so there you go, a nice simple linear regression analysis. Just a quick reminder about the difference between the standard error of the slope and the root mean squared error, because people get this confused a whole bunch. When I talk about the standard error of the slope, that is how far off my estimated slope is likely to be from the truth. It's kind of how far off I think what I measured from the data is likely to be from the true value in the population. So the standard error of the slope is a measure of how far off my estimated slope is from beta 1, the true slope in the population. The root mean squared error, which R refers to as residual standard error, is telling me about how well the regression is fitting the data. The root mean squared error is the typical size of the residual, how far points are from the fitted regression line. So two fundamentally different quantities. They both kind of sound the same when you talk about them, standard error versus root mean squared error. Very important to know the difference. Root mean squared error is the typical size of the residual. Standard error of the slope is how far off we think the measured slope might be from the truth.